In this video, we're going to go through the problems on worksheet number 1. The first problem tells us that we have a balloon that's absorbing heat and it's expanding and doing work, and we're being asked to calculate the delta U for the balloon. Delta U is calculated by adding the heat plus the work. So we need to figure out not just the values of the heat and the work, but also the sign. The balloon is absorbing 227 joules of heat. Because the balloon is absorbing heat, we know that that is a positive Q. Again, that comes from the word it's absorbing heat. So our value of Q is positive 127 joules. For the work, it tells us that the balloon is doing work, so that is a negative W. Also that it's expanding, that also tells us it's a negative W, because the balloon is losing energy as it expands and does work. So this would be a negative 325 joules. So all we have to do is add these up and get our value of delta U. 127 minus 325 is negative 198 joules. The next problem is pretty similar. We're again being asked to calculate the change in energy. We have information about heat being released. We could just start with that because it is releasing heat. This means that its sign of Q is negative. It's losing energy in the form of heat. It's not giving us the actual value of work, but it is giving us the change in volume and also the pressure. So we can calculate work from this information. In this volume change scenario, the problem tells us that the gas is starting at 30.3 milliliters, so that's our initial volume, and it's expanding to a final volume of 102.5. Our work equation needs these volumes to be in units of liters, so I'm just going to begin by converting this to liters. And so let's just go ahead and start by calculating our work. Work is negative P delta V. The pressure is 1.5. And the delta V is final minus initial, which is 0.1025 liters, minus 0.0303 liters. This is I'm going to do the 0.1025 minus 0.0303 times 1.5 atmospheres. This gives us a value of negative 0.1083, and the units are liters atmospheres. These units need to be converted into joules using our liter atmosphere to joule conversion factor. We want the liter atmosphere unit to be down on the bottom so that it cancels, and the joule unit to be up on top. The conversion factor that we're using here is 101.325 joules for every 1 liter atmosphere. And so this gives us, don't forget that negative sign, negative 10.97 joules. So now we're ready to plug these into the delta U equation. Delta U is Q plus W. We've already decided that our Q, the sign of our Q is negative, so that's going to be negative 87.2 joules of heat plus our work, which is negative 10.97 joules. And this gives us a total 98.2 joules for the energy change for this system. The last problem is asking us about calculating the heat evolved from 15.6 grams of zinc sulfide reacting. On the worksheet, I didn't put the delta H value for this problem, but you definitely need to have it in order to be able to solve the problem. This is like a unit conversion problem where we're converting from units of grams into units of kilojoules. So we're going to treat this like a unit conversion, and that means that we're going to start by writing the thing that we know. The thing that we know is 15.6 grams of zinc sulfide. We need to convert this into moles of zinc sulfide. We're going to do that using the molecular weight, which comes from adding the mass of a zinc and adding the mass of a sulfur atom, 97.5 grams per mole. After we have converted into units of moles, we can use delta H as a conversion factor between moles and kilojoules. We want moles of zinc sulfide to be down on the bottom of this conversion factor, and we want kilojoules to be up on top. To fill this conversion factor in, for the kilojoules part, we're going to be using the delta H value, negative 879. And for the mole part, we're going to be using the stoichiometric coefficient from the zinc sulfide. So this is going to let our grams unit cancel, the moles unit will cancel, and we'll be left with units of kilojoules. 15.6 divided by 97.5 times negative 879 divided by 2. We get an answer of negative 70.3 kilojoules.